You're running a small work cell where two similar products move through the same set of machines. Each machine has to be loaded, run, and unloaded, but one operator is responsible for handling the manual work across the whole cell. How do you balance machine capacity, operator time, and limited space between steps? And what happens when demand or product mix starts to vary? There's a model for that. Welcome to Model Monday, a series where we break down scenarios in different industries, organizations, and departments and explain how you can build a simulation of them in Process Playground. Let's model it. We're going to have two item types that go through this process. We'll call one Item 1 and we'll call the other Item 2. Now we're going to add a demand block and call it Demand Takt Time to establish our target pacing for the system, while also simulating natural variation. We'll start with Item 1, which has a time between arrivals that is normally distributed with a mean of 9 minutes and a standard deviation of 1. This means there will be an average of 9 minutes between each item, but with natural fluctuation. Some will arrive sooner than 9 minutes, and some will arrive later. For Item 2, we're going to have the time between arrivals that is normal with a mean of 14 minutes and a standard deviation of 3. There will be fewer Item 2s arriving in this process since there is a longer average time between arrivals. Next, these items that have entered the process are going into a queue, which holds the items until they are able to move on in the process. We'll call this queue backlog. Now we're going to create a special queue that will only allow one item to go through at a time, and we'll call this Q1 fixed length. The max items parameter allows us to limit the number of items allowed in this queue at once, so we'll set this to 1. Now we're going to add a loading step. We'll call this Load Step 1. The processing time for loading can be represented by a triangular distribution with parameters set to a half minute, a minute, and a minute 25. So I'll copy this block and move it to another part in the process so that we can keep those same parameters we have already set. We'll name this Load Step 2. We'll copy again, place it, and call this one Load Step 3. Now that we've modeled loading a machine, we're now going to model the automatic part. We'll create another activity block called Step 1 Auto, and this will represent the machine part of Step 1. Both items in this machine will be processed at the same rate, which will be a triangular distribution with a minimum of 2, a mode of 4, and a max of 6. Now I'm going to copy the load step again and use it to create an unload step with the same parameters. I'll rename this to Unload Step 1. And let's connect up all these steps. Great. I'm going to now copy this unload step and apply it to the other sections of our process. So I'll copy and paste and move it to Step 2 and rename it, and paste again and call this one Unload Step 3. Now we're going to create a second queue, which we'll call Q2 fixed length. And again, we're going to say that only one item can be in this queue at a time. And we'll connect them all up. For the Step 2 machine, we'll take out another activity block and rename it Step 2 Auto. This machine handles Item 1 and Item 2 differently. For Item 1, we're going to say that the machine processes each item with a time selected from a distribution that is triangular with a minimum of 5, a mode of 6, and a max of 9. For Item 2, it's also going to be triangular, but the times will be 4, 6, and 8. We're going to do the same thing where we create a queue called Q3 fixed length and limit it to only one item. And we'll connect this up to Load Step 3. We'll add our Auto step for 3, and we'll add unique parameters for each item. Item 1 will have a triangular processing time with parameters 2, 4, and 6. And Item 2 will have triangular with parameters 3, 4, and 7. Once we've unloaded the last step, we're actually going to add another queue here and call it Exit Signal, which will just act as a pass-through for our items on the way to the exit. And finally, we'll add the exit to signify the end of this part of the process. Now, each of these steps, 1, 2, and 3, can only process one item at a time. You can't load into a machine that's already working on an item. So we'll limit the number of items in part of the process by using a core pull block. We'll put the core pull block here and call this step 1 capacity. It's going to start at load step 1 and it's going to end at unload step 1. And we'll set this to be 1. We'll do the same thing for step 2 and step 3. We'll call this step 2 capacity and load step 2 and unload step 2. And we'll add step 3 capacity and we'll have load and unload. Great. So now we've limited the capacity at each of these steps. The final step is to add a resource. This will be a single operator who loads and unloads each machine on this line. We will assign this resource to each load and unload step. Normally, you'd want your priorities to be in reverse order, but since we have core pulls at each step, the priority order matters less. Once we close the popover, we can see the person is working here, 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 and here. Once we've set up the model, it's time to run it. We've set it to run for 500 minutes, and we'll set the number of runs to 10. By setting this parameter, we'll get summary statistics across all 10 runs to pick up on variation in the output. When we run our model, we can use the speed control down here at the bottom to control how fast or how slow the animation runs, as well as a scrubber for setting the specific time you want to see in the animation. We can see work coming in, the work in the machines, and the work getting loaded and unloaded. We can also see the inventory building up here, and ultimately we'd like to clear it. We can also look at our results. If we double-click on a block and switch the tab to results, we can see the statistics. How many did we get done in 500 minutes? And what was that total lead time? From the time the item arrived at this part of the process to when it exited, the average lead time is about 120 minutes. This includes all of the time the item sits in that backlog queue. When looking at our queues, we would be interested in the count of items that pass through, the average length of the queue over the course of the simulation, and the block cycle time, or the time spent in this particular block. Let's click Apply to all queue blocks to set these statistics on all of them. Let's take a look at the backlog block up here, which has a large number of items. We can see the average length over the course of the simulation was 18.73 items, and the average time spent in this block, or the block cycle time, is 92.86 minutes. This is the time spent waiting to get into the process. We can also take a look at some graphs by clicking on the backlog and opening up the queue length graph. And it's very clear our process is not keeping up with demand. If we look at this next queue, because we set the max number of items to 1, we can confirm that we only ever have 1 item. How about this queue at the bottom? We might be interested in how long items are spending waiting, and we can see from the block cycle time that it's about 2.41 minutes. When we open the graph, we can see the actual distribution of that wait time across the simulation. For our activity blocks, we'll analyze the runtime and the idle time. We'll zoom in a bit here. We can see that this machine is working about 47% of the time, and it's not running about 50% of the time. The rest of that time is blocked time, where the item is waiting to be unloaded by our operator. Finally, let's take a look at the utilization of our core pull and our resource. We are more interested in our utilization for the manual work resource block, and we can see that our operator was occupied 62.1% of the time. Depending on your goals, you can use the simulation to experiment with changes that affect utilization, block cycle time, total lead time, or other statistics. Because we set the number of runs for this model to 10, we have another toggle in the results. This allows us to see the aggregated statistics across all 10 of those runs and gives us a sense of the variability we might see in outcomes based on the variability of the inputs. The first number represents the average of that statistic across all 10 of the runs, while the second number is the standard deviation of that statistic across all 10 runs. This format also shows up in the table underneath the block. So in a nutshell, that's the work cell model. But the real value is in what you can experiment with. By modeling multiple products moving through the same machines, with one operator loading and unloading the equipment, you can see how machine time, manual labor, and limited work-in-progress space interact across the cell. And it's not just work cells. The same pattern shows up in lab testing stations, packaging operations, repair shops, or any process where similar work moves through shared equipment with limited space between steps. From here, you can start to ask real design questions. Do I have enough operator capacity to support the machines? Is the process limited by machine time, manual work, or space between steps? What happens if demand increases for one product more than the other, or if variability makes one step less predictable? Those are the kinds of trade-offs this model is built to explore.
That's the model. Now go experiment. Happy modeling!